Welcome back to my channel. Today we're gonna do the question find if path exists in graph. I previously did this question in my channel in DFS, and today we're just gonna do it in BFS, breadth first search. So the difference is breadth first search traverses the graph level by level, and it would visit all levels of neighboring nodes, before it proceeds to the next level. And DFS traverses the graph by depth, and then it would go into the final, very leaf node before it checks out the neighboring, the other path that it's possible. So usually the advantage of BFS breadth first search is it will always find the shortest path between two nodes. That's like the same weight, and considering it's bidirectional, the two nodes in the shortest path possible. For DFS, it's generally not known to do that because DFS is like going by depth first, but BFS by level, it will always find the shortest path. Whenever we do reach a target node, that is guaranteed to be the shortest path. So let's start. Let's look at this question. Find if path exists in graph. There is a bidirectional graph with n vertices where each vertex is labeled 0 to n minus 1 inclusive. The edge in the graph are represented as 2D array edges, where edge UV denotes a bidirectional edge between U and V. Every vertex pair is connected by at most one edge, and no vertex has an edge to itself. You want to determine if there is a valid path that exists from vertex source to vertex destination. Given edges and integers and source destination, return true if there is a valid path from source to destination, or false otherwise. So there's 3 nodes, and these are the edges. Source is 0, destination is 2. Returns true because it can go from 0, 1, 2, or 0, 2. And this one is false. It's looking for source 0 and destination 5. 0 and 5. It's not within the same, it's not connected, it's not from the same component, so it's going to return false. There's another way to solve this, also using union find, so you can see if they have the same absolute root, and if they do, then there's a path between them, but if they don't, then there's no path between them. But today I'm just gonna do BFS. So to span my adjacency list, I'm gonna use default dictionary. So I'm gonna do from collections import default dictionary, and then let's span the adjacency list first. So adjacency list equals default dictionary of lists, and then for node 1, node 2, and edges, we want to span our adjacency list with these edges. So adjacency list node 1 dot append node 2, and then adjacency list node 2 dot append node 1, because this is bidirectional. And now we can start writing our BFS. So for BFS, we always have a queue, and queue, we're gonna start our queue with the beginning node, which is start, and then we can also have a visited set, where we keep track of all the visited nodes that we've seen, so we don't repeatedly visit them. And now we're gonna do while queue, and then we can pop our node from our queue, which would be the first node, and we're gonna pop it from the left, pop 0, because for the queue structure. And then after we pop it, we can check if this current node equals, actually for the visited, let's have it initialize with the start node so we don't have to mark it here. So if node equals the end node, then we can just automatically return true because there is a path that exists between them. And otherwise, we can go through the neighbors. So for neighbor in the adjacency list node, and we can do if neighbor not in visited, then we can do visited dot add neighbor, and then queue dot append neighbor. So if it goes through all the neighbors level by level, and at some point it finds the end node, then it will return true here. But if we've exhausted our entire queue, there's no longer nodes that we haven't visited, then we just return false at the very end, meaning there's no path between those two nodes, like here. Please let me know if you have any questions. And oh, by the way, the time complexity of this is time is O of v plus e, where v equals the number of vertices and e equals the number of edges. And the queue would just be adjacency list. So it would be OV for the queue because it depends on how many nodes there are. Please let me know if you have any questions, and thank you so much for watching.